Hello everyone, welcome back to the MOOCs course on Advanced Analytical Technique. Today we are having the fourth lecture of the third week, in which we are going to cover the sample preparation methods of the ICP AES technique as well as the possible interferences, both the spectral as well as the non-spectral interferences that may create some complications in the analysis of the given sample. So let us start this discussion with the method of sample preparation. Of course, the method of sample preparation has a strong influence on the results of a particular analysis, especially in case of ICP AES. The method which we are going to use has a strong influence or the strong effect on the results on especially in case of atomic emission spectroscopy and ICP. The sample preparation method has a strong influence on the final results. As you can see here, the procedure of this sample preparation depends upon the nature of the sample, and even more important is the sample matrix from which we are going to extract the sample, or from the matrix or the type of matrix from which we are going to make the studies. Of course, the concentration of the analyte present in that matrix is very important. Sometimes the target analyte is present at very low concentrations, even in traces, and therefore for such a sample we cannot go for an atomic absorption spectroscopy technique, and therefore we have to go for ICP AES, or I should say ICP OES techniques. Similarly, in case of metals which do not atomize or excite easily, for example high melting point metals like we have tungsten W, or we have osmium, rhenium, these are the metal and the refractory metals which do not undergo atomization easily. So for those metals it is quite difficult to perform a precisional analysis with the help of atomic absorption spectroscopy. Therefore we have no option but to go for AES, and in that case also for AES, for these metals we cannot go for direct aspiration because they require very high temperature, and they are only possible to be analyzed with the help of an ICP connected with an OES or an AES technique. Of course, as I said, the choice of method is mainly depends upon the sample matrix. For example, sometimes we have matrix which is a liquid matrix, sometimes we have solid matrix. Now in solid we have different types of matrices. For example, we may have a soil matrix from which we have to analyze the type of elements present. For example, we have a piece of land which is very close to an industry, and there is a history of soil pollution in that particular area by the nearby industry, and we have been given a task to identify the type of heavy metals present in the soil, so that we can identify whether that soil is good for agriculture or some other kind of activities or not. So in that case we have to collect soil sample, and then we have to extract, because we cannot inject the soil sample as such, or we cannot just dilute the soil by mixing it in water and then inject. There is a separate method by which we can extract the elements present in the soil sample, and then only we can do the analysis. Sometimes even in solid we may have rock samples, which is even very difficult to digest it and to extract the samples present in it, especially the target analyte. Similarly, in case of liquid we have different viscosity of based sample. Similarly, in case of liquid we have different viscosities. For example, if river water is there, the viscosity is different, while in case of a blood sample the viscosity is totally different. And similarly we have a cola sample to identify in that case as well. And for example, we have a cola sample, a soft drink, there also the viscosity is quite different. So we have different physical states of the sample. It may be liquid or it may be solid. Sometimes solid are those solid which are having very high density, like in case of rock, while soil it is not very dense. And then similarly in case of liquids we have blood, we may have juice samples, cola, or simple water, tap water, or we have simply water like groundwater, or maybe the surface water coming from a river. So different types of sample, their physical states, their viscosities plays an important role, which must be kept in mind before selecting a process for sample preparation. For example, in case if we are having a normal tap water or a groundwater, we directly filter that sample so as to remove all the suspended impurities, because those impurities ultimately causes clogging of the column, especially in the nebulizers. So those impurities causes clogging of the pores of the tubes of nebulizers. Therefore, we always filter the sample, even if it is a clear solution, then also we filter it so as to avoid all the chances of clogging of the tubes of nebulizers, to keep all the components working efficiently. And however, in case we have some other sample which has high viscosity, or even if the sample is solid, we have to go for digestion methods. And there are two methods that are used for digestion. One is called as the dry method, and the second one is called as acid digestion method. In the next few slides, we'll discuss about these two methods in detail. The dry method, this method is based on alkali fusion technique. Now, what is this alkali fusion? In alkali fusion, we mix the sample with a strong alkali. We may use NaOH. We may also use sodium carbonate. We can also use Na2O2. And when the sample is mixed, then this sample is heated at high temperature, so that the alkali at this high temperature reacts with the sample and digest it and extract all the elements that are present in it. This method basically burn the sample into ashes. It basically burned the sample into ashes, and now those ashes, which are in the form, of course they are in the form of powder. Now from those ashes which are in the form of powder, we add acid, and that acid extract the elements present in it, and then we filter out the acid, and finally that acid which is already, and finally the filtered, and finally the filtrate is ready for injection into the nebulizer of ICP OES. So what do we do? First of all, take the samples. This method is especially used for soil matrix, even for alloy sample. Now, for example, in case of alloy, we want to analyze the different types of metals present in an alloy, and now alloy, which is metal, it is very difficult to digest it. So for those samples, what do? Is we take the sample, mix it with a strong alkali, and then heat the content, heat at high temperature, so that they all burn into ashes, or they are finally digested completely to form a paste or a powder. Then to this paste or powder, we add acid that extract the sample. We add acid, and then we add acid into it, and finally that acid extract the elements. Now we cannot directly inject this acid into the nebulizer. We go for filtration, or we centrifuge. We go for filtration, or we simply centrifuge the sample to remove all the suspended materials, suspended impurities, ashes, powder, or maybe any soil sample is still left, and then the filtrate is ready for injection into the nebulizer for the analysis of for the formation of emission spectrum and further studies. In this method, the losses due to volatility and insolubility are significant, because there is some possibility that in some cases, for example, if you are mixing the oil, it is not completely mixed and with the alkali, and if the mixing is not proper, which it means not the whole sample will not be digested, and in that case the extraction amount of the elements in the acid is very low. So we can still analyze and detect those samples, but if the amount is low, the quantitative analysis will not be reliable. So that is why this is the main disadvantage of this method, that it has some volatility and insolubility issues. Sometimes due to high temperature some of the metals evaporates. When they evaporates, the detection will not be possible. In second case, if the elements are insoluble, or if the sample matrix is insoluble in the base, even after proper mixing or giving sufficient time to interact, some of the amount will still some of the amount of the sample matrix will not react, while only a fraction of its amount will react, resulting into low concentration of the elements that are finally present in the ashes. And when we extract it, the sample elements, and when we extract it with the help of acid, the target analyte will still be present in the target analyte will still be at in the target analyte will still be at lower concentration in the acid. And then, although we can detect these low concentration because the instrument is very sensitive, we have very good detection limits, but of course the quantitative analysis is compromised. We cannot rely on those results for quantitative analysis. So as I said, this technique is very useful for soil matrix, alloy sample and rock analysis. Unless and until we are maintaining good solubility, the technique is very good. Then the other method is the acid digestion method. So the previous method was the dry method where we are using alkali fusion. Now in this method it is called as the acid digestion method. In this method the sample is digested, or the sample is mixed with strong acids like HNO3, HCl or HClO4, and when in this method the sample is digested, or it is mixed with strong acids like HNO3, HCl and HClO4, which causes the dissolution of the sample matrix via oxidation or reduction. Sometimes it causes oxidation or sometimes reduction, but ultimately it dissolves the sample matrix, and thereafter when the digestion is complete, the sample still have some suspended impurities. Therefore the sample is filtered to get a clear solution, and that clear solution can be used for analysis and that clear solution can be used for analysis using ICP AES. However, there are certain points which must be kept in mind while using the acid digestion method, because for example, if we are using HCl in this method for the digestion of samples and our sample contains SN or AS, then there is a possibility of formation of this SnCl4, because when SN is treated with HCl, it forms stannous chloride, which when SN is treated with HCl, it forms stannic chloride, and these chlorides are very volatile and they evaporate. Ultimately the sample is lost. Therefore we have to be very cautious that if our sample has some history of tin or even AS, then if we are using the acid digestion method, of course still we can use the acid digestion method, but in that case we cannot use HCl as the acid for digestion, although we have flexibility in this method. We can go for HNO3, even if we can go for H2SO4, and even a weak acid like H3PO4, even a weak acid like H3PO4 can also be used, but sometimes we use H3PO4 because there are few reports in literature which says that H3PO4 sometimes due to its viscosity affects the temperature of the plasma or destabilizes the plasma, which ultimately hampers the analysis. So H3PO4 can be used, but in very few cases we use H3PO4. Most of the time we either use HNO3 or HCl. Even H2SO4 and HClO4 can also be used. Further, the amount of acid should not be very high, because if the amount of acid is very high, the traces of the acid may create some interferences in the plasma, or if the amount of the acid, it may destabilizes the plasma. So the amount of acid should not be very high, but on the other hand the amount of acid should not be low, because if the acid amount is low But on the other hand, the amount of acid should not be very low as well, because if the amount of acid is low, the possibility of complete digestion will be lost, and if there will be no and if the digestion is not complete, the actual concentration can never be detected, and we again compromised the quantitative analysis of our samples. So the amount of acid should be moderate. It should be sufficient to completely digest the sample matrix. However, it should not be in higher volumes, because higher volumes causes destabilizing the plasma, which ultimately affects the spectral analysis. And as I just mentioned, the amount should not be too low, because it affects the digestion process. Some of the acids, like I mentioned that H3PO4 has been reported by several scientists that it causes destabilization of the plasma. It interacts with the, it reacts with the, it affects the plasma. It causes to destabilize the plasma or reduces its temperature because of its viscosity. Therefore, an order of preference of the acid usage has been given. First of all, we go for an HNO3 because it does not react. Further, if the amount of this HNO3 is moderate, it can, on one hand, it can completely digest the sample, and if the amount is moderate, it will not react or destabilize the plasma. Therefore, the first choice is HNO3 because it does not react with metals like SN or AS to form their volatile salts, just like we have in case of HCl. When it reacts with tin, it forms volatile chlorides of the tin. Then if even HCl we cannot use, then we go for HClO4, then finally H2SO4 and H3PO4. So this is the choice of preference or the order of preference, where we always put HNO3 on top because of its high strength and low possibility of the reaction of this acid with our metals to form their volatile salts. Clear? Let's move to the next slide. Now let us discuss the interferences in the ICP. Although ICP is one of the most versatile technique, it is one of the most sensitive technique, but still it has certain interferences. As I said that since it is a versatile technique, it provides very high temperature, and because of that high temperature, we always have all the samples that are possible in we always have all the elements that are present in the sample matrix to be excited and to be analyzed. But still there are possibilities of several interferences, although these interferences can be minimized, which ultimately makes our results more reliable as well as reproducible. We have to keep those points in mind to reduce these interferences. So, as I said, ICP is a robust and sensitive technique, but it has some interferences. Because it is very sensitive, it may detect impurities as well, or it may detect samples that are present from the previous run. So these interferences may cause complications in the spectra. Sorry, these interferences may cause complications in the spectra, sometimes due to excessive peak, sometimes due to peaks that are very close to each other. For example, these two peaks, and in case we have sometimes a shoulder peak, these types of peaks are known as shoulder peaks. So they create some complications in the study. Now, this interference may occur at any stage. This interference may occur at the time of even sample preparation. So the sample preparation should also be done with extreme care. Otherwise, we may have some impurities in the sample, or we may have some foreign materials in the sample that ultimately causes new lines which we were not expecting. We will get those lines in the spectrum as well. So interferences may be possible during the time of sample preparation. These interferences may also be possible during the analysis when we are doing nebulization and then we are doing atomization and excitation. So these interferences are also possible during the analysis. When it is being done At sample preparation level, it may be due to the method we are using, it may be due to human error, or it may be due to matrix effect, means the type of sample. Now broadly these interferences are divided into three categories. First is called the spectral interferences, and then we have two non-spectral interferences. These non-spectral interferences are divided into physical interferences and chemical interferences. Let us discuss these interferences individually. Or the spectral interferences or spectra interferences, they are caused by any of the reasons. For example, occurrence of the peaks or lines belonging to impurities. For example, if the sample contains some impurities which we are not aware of, or if the nebulizing column may have some sample left out from the previous run, where we are again injecting the sample, and in this column, where now from this point it is being injected into the plasma. Now in this column we have traces of a previous run. Then when we inject the new sample, or when we insert the inlet pipe of nebulizer into the new sample, and the sample is being sucked with the help of peristaltic pump, this sample mixed with the previous run elements present over here in traces, and they finally enters into the spray chamber and then into the plasma. So because of the some elements from the previous run, we may have some new peaks. They are called as impurities peak. So these peaks causes complications because they are new peaks and we are not aware of. So it causes spectral interferences. Sometimes few lines are very close to each other. Some of the elements have the emissions line. Some of the elements have emission lines that are very close to each other, which causes ambiguity in the analysis. Or sometimes we completely messed up and we consider a line which is given by some other element. Sometimes two emission spectral lines given by two elements are very close to each other, which causes ambiguity. Or in some cases we may confuse that we thought that the peak or the spectral line belongs to one particular element, but since it is very close to another component, that peak actually belongs to the other component, but we are misinterpreting that peak, but we are misinterpreting that peak, and it ultimately needs to be avoided. Then the third type of spectral interferences are the background radiation. For example, the light coming from any other source. So the place where this analysis is being done, it should be completely free from stray lights. There should be no stray lights, and sometimes because of highly concentrated elements or the highly concentrated sample, we may have excessive concentration which causes very high intensity light radiations. Sometimes radiations are emitted because of the formation of some molecules. For example, when we have some molecular ion peaks present, for example, we have some molecules formed during this atomization and excitation, and those molecules emit some kind of light radiations. So we have stray lights which causes some new peaks, some extra peaks. So we have stray lights which causes some additional peaks into the spectrum, thereby hampering the analysis. And the last one is the recombination phenomena. Recombination means when we are atomizing and exciting the samples, when a molecule is converted into its individual atoms and those atoms are being excited, sometimes there is a possibility that those atoms combine again to form the original molecule, and since it forms molecule, then the characteristic peak of those atoms would be missing. Then the characteristic peaks of those elements would of course be missing, because we do not have the element present in its pure form. Now the element has recombined with other components to form the molecule again. So we missed those lines belonging to the pure or the characteristic spectrum of that element. Say for example, in case of copper emit light radiation at 515.323 nanometers, while the argon gas, which is used for plasma, and this gas is also present in the plasma in the form of cation along with electrons, and as I said yesterday that few molecules of the air gas is still present, which do not ionizes completely, because which do not ionize because the gas does not ionizes 100%. So these also create some emission spectrum. The spectrum of this AR falls at the spectral line of this argon falls at the spectral line of this argon comes at 515.139 nanometers. These two are very close to each other, because if we are plotting the spectrum, and 500 we have all these digits same. We have 515 and 515, so we have sometimes very close peaks over here. For example, here we have some other element at 300. Now this is 515, and we have two peaks at 515.3 and 515.1. This is very difficult to resolve. So these two peaks come very close to each other, or I should say the peaks gets overlapped, and it is very difficult to completely resolve these two peaks that are so close to each other. Sometimes, as I said, there is a formation of metal oxide. However, in case of ICP, there are very low chances of formation of metal oxides, because there are two reasons. First of all, we are not using oxygen gas in this particular case. We are making the aerosol with the help of inert argon gas. So no oxygen or air is being involved in this particular study, so the possibility of metal oxides is minimum. And if in any case metal oxides are formed, then the temperature is so high, because we can go up to 10,000 degree Kelvin, and the place where we are making the analysis, I told you yesterday in the previous class that when the plasma is formed, when this from the torch we have these coils and plasma is formed, initially the temperature is very high, 10,000 degree Kelvin. But we can do the analysis here, but it is very bright region, because plasma emits a continuum of bright lines. So we move a bit upward, and at a distance of 2.5 to 3 centimeter, where the region is completely transparent, we do the analysis, and at this particular point the temperature is around 6,000 to 7,000 Kelvin. But still this temperature is even very high, that even all metal oxides undergo atomization and excitation at this particular point. So of course there may be this interference, but the chances of metal oxide interference in ICP are very low, because there is low possibility of even formation of these oxides, and if they are formed, they will undergo excitation or atomization, no problem, because of the very high temperature. Yes, but if we are not using ICP, we are using AES with flame ionization, then of course, because flame, in case of flame we are using oxygen as an oxidant, and the temperature is also not very high. So if there is of course a possibility of formation of metal oxide, and once these metal oxides are formed, they are thermally stable, so they do not dissociate at that particular temperature which is achieved by a flame. Then even some undesired species are formed. This is a possibility, as I said, because sometimes the molecules atomize into the individual atoms for excitation, and those atoms again recombine to form the molecule, or they sometimes react with the solvent component and form undesired species, because of which we may have extra peak, or these undesired peaks may affect the plasma, causing fluctuations in the plasma. Sometimes even we have a doubly charged samples, even in the spectra of an element. For example, we have iron. If we are analyzing a pure sample of iron, or if we are analyzing an alloy, there, for example, stainless steel which contains iron, and that is Fe in zero state. But if we compare the spectrum of Fe with ferrous and ferric ions, they are quite different, although they all belongs to iron, but their oxidation states matters, and by changing in the oxidation state we have different spectral appearance. Then we have background emission must also be adjusted to get specific results, and background emissions can be adjusted by doing a blank run. Means the same solvent is being used. For example, if we have a soil matrix where we are going to do the analysis of the elements, and we are using either the dry method using our alkali fusion, or we are using the acid digestion method. In both these methods, at the end we recover the elements in the acid, and then that acid is being filtered, and finally the filtrate is then injected for analysis. So in order to reduce this background emission, first of all, without having any soil matrix digested, that pure acid should be injected so as to create a background spectrum, and then the acid is used for digestion of the soil matrix, and finally the filtrate is injected, so that in the second run we subtract or we exclude the background emission. So background emission are of course causes interferences every time, and these background emission can only be reduced or avoided by doing a blank run and then excluding those background emissions. Just we do as we do in case of simple chemical analysis, which we do in chemistry laboratory, like titrations. While doing titrations, we always do the blank run and then subtract the volume of the blank with the volume of the sample in which analyte is present in that blank, so in which the analyte is present in the solvent. And for in case of blank, we only use the solvent without the analyte. So get in that case also, in case of titrations, that is called as the background noise removal, or the background, or to or in that case of, so in case of that titration as well, we remove the background noise just by doing a blank run. So in this case also the background emission can be removed by doing a blank run. Then comes the physical interferences. These physical interferences are related to the nebulization and the flow of samples. Some nebulization means sometimes the aerosol is not formed properly, or the aerosol may have different size of the droplets, means the droplet size is not uniform. So if we have very large droplets suspended in air, so if we have very large droplets suspended in argon gas to form aerosol, large droplets have large volume of solvent which destabilizes the plasma. Therefore the nebulization should be very proper. Further the flow of sample is also important, because if the sample is being injected at very high flow rate, what does it mean? It means that large volume of sample will be sprayed by the spray chamber into the plasma. Now these large volume causes some of the sample will undergo atomization and excitation, while rest of the sample will fall on the torch, which ultimately reduces the plasma, or it destabilizes or causes fluctuation in the plasma. So these interferences refers to as the physical interferences. One more thing which creates some sort of physical interferences is the difference in viscosity of the solvents. Sometimes if the solvent is very viscous, it is very difficult to convert that solvent into those small uniform aerosols, sometimes the viscosity of the solvent or the surface tension is very high. In that case, it is very difficult to convert that highly viscous solvent into a uniform aerosol. And as I said, if the aerosol is not uniform, if the droplets are very large, or if the droplets are very viscous, because viscous droplets may cause difficulty in excitation. So this ultimately causes physical interferences. And the last one, however, this physical interferences due to surface tension or viscosity can be reduced by diluting the sample. By adding some other solvent, we can reduce the viscosity or the surface tension. And as I said earlier, there may be some peaks due to the deposition of sample in the nebulizer pipe because of our previous run. So before we are making an analysis, we first of all pass the solvent 2-3 times, so that the tube will be completely washed out. Even in case of chromatographic techniques, when we are doing those techniques, or like these spectroscopic techniques, we always do blank sample runs between two individual sample analysis, so that the traces of the previous sample will be completely removed and the analysis is going to be free from physical interferences. So this type of so this type of interference, which is due to peaks from the previous run, they can be minimized or completely prevented by flushing the system with solvent. We have to pass solvent 2-3 times to create a plane spectrum of the solvent, and in this way the solvent passes through the tube and causes washout or flushing of the previous and causes flushing of the previous samples. And this is the chemical interferences. Chemical interferences are and this is the chemical interferences which occur due to solute vaporization and ionization effect. Sometimes they are also due to the formation of compounds with low atomization efficiency. What do you mean by atomization efficiency? Atomization efficiency means there is a formation of those compounds which are thermally very stable and they do not atomize, means they do not get dissociated from their molecular form into individual atoms. This happens when we have samples which either recombine when atoms are formed and they recombine back to form the molecule, or in cases when we have very highly when we have samples with very high thermal stability. Although with ICP this can be minimized. Now solute vaporization. Solute vaporization means when the solute vaporizes before reaching to the plasma. In that case, because of the low vaporization of the solute, we may sometimes or so in that case, because of the low vaporization of the solute or the low vaporization of the target analyte, it vaporizes in ground state only. Before getting excited, it vaporizes in ground state and it will not emit any spectral lines, and because no spectral lines and because no light is emitted, there will be no peak of that sample in the final spectrum. So low vaporization causes quick evaporation of the sample even before it is excited, and it vaporizes in the ground state only, resulting into no emission spectrum. Then there are ionization effect. Sometimes the sample do not ionize because of its thermal stability, or sometimes the sample ionizes very fast. So if it ionizes very fast, some of the data or some of the lights is not being read properly, and the results are not very reliable, or I should say the results are not reproducible, because when we do the second time, there may be because when we do the analysis second time, the extent of this effect may vary, and we have different height of the peak, which makes two different data, which creates two different data, which gives two different concentration values. So it basically like that. So we can say that in that case the results are not. So if we are doing for example previous cut, so in case of ionization interferences, sometimes the sample do not ionize easily because of its high thermal stability, or sometimes the sample ionizes quickly, so all the spectral lines are not being read properly. So it creates low reproducibility in the result, because when we are doing the second time, the extent of this interference may not be the same, so it may give a peak of different height, and we have two different values of the concentration. So I can say that these chemical interferences causes low reproducibility. These ionization effect may also occur due to shifting of ionization equilibria. For example, if we have some samples which have very high, which require, for example, if we have certain samples which require high temperature for ionization, but on the other hand we have some more elements present in the sample that ionize very quickly. So because of very quick ionization of these samples, which create excessive electrons and ions in the plasma, there is a possibility that the ionization of high melting point elements, because of very high concentration of, because of very quick ionization of these elements, which creates extra cations and electrons, the ionization of high melting elements is affected. So this is a type of ionization effect. So it ultimately causes difficulty in, so it ultimately causes the possibility of missing that particular element. It basically causes the possibility of missing that particular element, or its concentration is not well calculated, or its concentration is not well determined. We can in that, or its concentration is not determined properly. However, by carefully controlling the operating conditions, the incident power, and by controlling the temperature, as well as by making the plasma stable, by controlling the flow rate, we can control these chemical interferences, leading to reproducible and reliable results. With this, the interferences and the sample preparation method is over. Thank you very much.